Welcome back. Today I'd like to talk to you about double integrals and polar coordinates. And to start out, we should kind of just do a quick review of polar. I'm not going to go through all of polar coordinates, but we should certainly recall these facts from polar is that r squared is x squared plus y squared, that x is r cosine of theta, and that y is r sine of theta. And if this does not sound familiar to you, then I would highly advise you go back and watch previous videos about just basic polar coordinates. Okay, but what we're going to be talking about today is what if we have a surface but the region over which it falls, instead of being a rectangular region or some type 1 or type 2 region, is a region that's best expressed in polar. So let's think about this for a second. Polar regions, I'm just going to draw kind of a very typical polar region, is let's think about a polar rectangle. So a polar rectangle, I'll draw it like this. Okay, and let's say that this is the region that I'm talking about in here. I'll call this the region R that we're interested in. And this is what we would call a polar rectangle. And what I mean is that this ranges between two theta values. First of all, we have this theta value from 0 up to what I'm going to call theta is equal to some value alpha, all the way to, here's another theta value. This is theta equals, let's call this one beta. So this is alpha. This is beta. Okay. And then we have some r values, and this r value here is going to be, if we completed this circle here, this is going to be r equals a to a radius value of r equals b. So this polar area is in between r values of a and b from theta value alpha to theta value beta. So we get this polar rectangle here. Okay? So let's say this, let me write this down as a definition. This region R is a polar rectangle. All right. Now, what I want to do is take any region that's in the xy plane and I can break it into polar rectangles. So what I'd like to know is, okay, how would I find basically the area inside of a polar rectangle? What is the area inside of that polar rectangle? Well, what I want then is, typically when we, let's say I'm breaking some region up into little polar rectangles. So let me draw another picture. And let's say we've got some region here. And I'm breaking this region up into little polar rectangles. Okay, so any region, I could start breaking it up into little polar rectangles as an approximation. And now let's just take a look at one of those polar rectangles. I'll fill one in to say, what if we took a look at just this one that I'm filling in? Okay, so if I blew that up, I have one polar rectangle. That is this guy. And typically what I do is if I want to find the area over that polar rectangle, then I want to take the area inside this base and multiply it by some height. And that height is determined by a special point that I pick inside of that polar rectangle, and I call that point r sub I star theta sub j star. Okay, so I pick a radius value, I pick a theta value, and I get this point, and that point is going to help me determine the height of the surface over this little polar rectangle. Okay, so what I want to do is I want to determine, well, what do I want my r sub I star to be? I'm just going to have my r sub I star be the middle of this. Okay, so this is my bigger radius, this is my smaller radius. I want it to be right in the middle of those two. In other words, what I'm going to do is I'm just going to take half of r sub I minus 1 plus r sub I. Okay, so I'm just going to average this r value right here and this r value right here to get my r sub I star. Okay, similar for my theta sub j star, I'm going to just average this theta value and this theta value to get me this middle theta value, which I'm going to call my theta sub j star. So theta sub j star is just going to be 1/2 of theta sub j minus 1 plus theta sub j. So just take the average. So once I've got this r sub I star and this theta sub j star, which I'm just basically saying is this center point right here, then I can talk about, well, what's the area? I want to take the area of this little piece. So what is the area of a little piece like that? So I'm going to call that area delta A sub ij. Well, if you remember from polar, the area of a sector of a circle like this is, if you took this all the way back to the origin, or you took this guy all the way back to the origin, then the sector of the circle, including this little piece, would be 1/2 r squared theta. So what we need to do is we need to take the big piece, including this stuff, and then subtract out this little sector. Okay, and that will just leave us with what's inside of this polar rectangle. So what I want to do is I want to take 1/2 of r sub I squared times delta theta sub j, okay, which is the area of this big piece, and then I want to subtract out 1/2 of r sub I minus 1 times delta theta sub j, which is the area of this little piece. Okay, I'm making a mess out of this, but now let's erase some of this to just clean it up a little bit. So again, I'm looking at this little sector. Okay, and this is my point. Okay, so if I want the area of this little piece right here, this is how I'm going to find it, right here. All right, so now let's combine this into one statement. I could factor out a 1/2, And I could also factor out delta theta sub j, but what would be left over is r sub I squared minus r sub I minus 1 squared times delta theta sub j. Now that factors because it's the difference of squares, so I get that this is 1/2 of r sub I plus r sub I minus 1 times r sub I minus r sub I minus 1 times delta theta sub j. Now look at this. This first piece, I've seen that before. It's right up here. So this is equal to r sub I star. Okay. And what is this? Well, that's the change in the r direction. So I'm just going to write this as delta r sub I, and then this is delta theta sub j. So the area that I'm looking for, a small change in the area, or one of these little polar rectangles, amounts to, pick a unique middle radius point, multiply that by a small change in r times a small change in theta, and that will get the job done for us. Okay, how is this helpful? Well, what I want to figure out is I want to look at the sum I going from 1 to m of sum j going from 1 to n of f of x sub ij star y sub ij star delta a sub ij. Okay, this is what we had before, and this is what we called a double integral. Now notice I'm in rectangular right now. I'm not in polar. But I can make a switch to polar. How would I make that switch? Well, in the following way. So the summations, I have sum I going from 1 to m, sum j going from 1 to n of f of, well, x sub I sub j star. Well, what is that? Well, it's r sub I star times cosine of theta sub j star, if you consider that xy point to be the middle of some polar rectangle. Then you can think of it in this way. I'll just convert this point into a polar point. Okay. Similarly, I'll convert the y into r sub I star sine of theta sub j star. And then I multiply that by the area. Okay, the area of the piece that I'm working with. But I just said that the area of a piece in polar is going to be r sub I star times delta r sub I times delta theta sub j. Okay. Then we would take that and take the limit as the maximum of the delta r sub i's and the theta delta theta sub j's go to 0. Okay. So now if we looked at this, here I'll just erase this for a second. Now what we want to do is we want to take this thing and take the limit as the max between the delta r sub i's and the delta theta sub j's goes to 0 of this thing. Okay? So if we take that limit, what we end up with is a double integral. And that double integral just happens to look like the integral from alpha to beta of integral a to b of f of xy. But in this case, xy is now in the form of r cosine of theta, r sine of theta. So we'll plug in r cosine of theta for x's, and we'll plug in r sine of theta for y's. And then we get this guy, which gives me an additional times r. And then delta r sub I just becomes dr, and delta theta sub j just becomes d theta. So we take this big Riemann sum and we turn it into a definite integral that looks like this. Okay? So this is how we would find the volume under a surface where the region that I want to look at actually works better in polar. So if I want to calculate volume using a polar base region, this is the formula that I want to use for the integral. Okay, let's do an example. The big thing to remember here is this little r. That's the thing that can throw us off if we're not being careful. Okay, so an example. Let's evaluate the double integral over the region R of 3x plus 4y squared dA, where R is the region in the upper half plane bounded by circles x squared plus y squared equals 1 and x squared plus y squared is equal to 4. All right. So first let's just draw our region and see what the region looks like. It says it's in the upper half plane. So here's my x-axis, here's my y-axis, and I've just drawn the upper half plane. And the circle x squared plus y squared equals 1 is just the circle of radius 1 centered at the origin. So there's my circle of radius 1. And then I also have a circle of radius 2. There's my circle of radius 2, also centered at the origin. And so the region that I'm thinking of right here is everything inside of this region. That's my region R. Okay, so now I've kind of got to think about this for a second. Is if I'm setting this up as a double integral, I know I want the outside integral to be the thetas that we go through, and the inside integral to be the r values that we go through. So if I start my thetas start here at 0, so this is theta equals 0, right? And it ends when theta is pointing out this way, which is theta equals pi. So I'm starting with theta is 0, ending with theta is pi. So I'm getting all of this stuff between 0 and pi. So 0 to pi. Then I want to say, what does r range from? Well, r starts at 1 and goes to 2. So from 1 to 2. I don't want this stuff in here. That would be the stuff from 0 to 1. I don't want that, right? So now what do I put in? Now I put in the function. Here's my function, but I don't want to put it in x's and y's. I want to put it in r's and thetas. So instead of having 3x, I'm going to have 3r cosine theta plus 4r sine theta, or y, and the y is squared. Then I need an additional r to be in there, so multiply that all by r. Then we end up with dr d theta. And this is the integral that I need to compute. All right, let me erase this and we'll do it on the next page. Okay. So I have double integral, and we said we're going from 0 to pi, from 1 to 2, of 3r cosine theta plus 4 times r sine theta, quantity squared, times r dr d theta. Okay, let's rewrite that. It's integral from 0 to pi, integral from 1 to 2 of, okay, so first of all, I need to distribute this r right here in. So this is going to become 3r squared cosine of theta. Oh, sorry. Looks bad. Cosine of theta. And then the second piece, I need to square that, so that will be plus 4r, okay, 4r cubed sine squared theta, because I still need to distribute this r in there. And then that will be dr d theta. Okay, now I think we're ready to go. First, we're integrating with respect to the variable r. So let's do that. So I'm going to be doing this inner piece. All right, so the integral from 0 to pi just hangs out. And inside I get r cubed cosine theta plus r to the 4th sine squared theta when I take an antiderivative, evaluated from 1 to 2 d theta. Now plug it in. What am I plugging in for? I'm plugging in for r. So I take 2 and cube it, which is integral 0 to pi of 8 cosine theta. And then I take 2 to the 4th, which is plus 16 sine squared of theta. And then I want to subtract, plugging in 1. So I just get cosine of theta plus sine squared of theta. All of that d theta. Okay, let's simplify a little more. I get integral from 0 to pi. Let's see, I have 8 cosine of thetas minus 1 cosine of theta is 7 cosine of theta. Then I have 16 sine squared thetas minus 1 sine squared of theta. So this is plus 15 sine squared theta. All of that d theta. All right. Now, I know the antiderivative of cosine theta easy enough. The antiderivative of sine squared theta, I actually need to use a half angle identity. So let's do that. I'm going to rewrite. So using a half angle identity instead of that sine squared of theta, I'd get that this is equal to the integral from 0 to pi of 7 cosine of theta plus 15 times 1 minus cosine of 2 theta over 2, all of that d theta. All right, let's take an antiderivative. The antiderivative of 7 cosine of theta is just 7 sine theta. Okay, and then I get a 1/2 here times 15, so that's 15 halves. And the antiderivative of 15 halves is 15 halves of a theta. And then I get minus 15 cosine of 2 theta over 2. And the antiderivative of negative 15 cosine of 2 theta over 2 would be minus 15 sine of 2 theta divided by 4. All of that evaluated from 0 to pi. All right, so let's plug in pi. Sine of pi is 0, so this first one's 0. Then I get 15 pi over 2. Then sine of 2 pi is also 0, so I get plus 0. Minus, now I plug in 0 and I get 0 plus 0 plus 0, so 0. So I just am left with 15 pi divided by 2. And that is the volume under that curve. So that's very nice. Okay, so basically what all of this is saying is the following: that if f is continuous on a polar region of the form D, which is equal to the set of all points r theta such that alpha is less than or equal to theta is less than or equal to beta, and we have, let's say, h1 of theta is less than or equal to r is less than or equal to h2 of theta, then we get the following: that the double integral over this region D of f of x comma y dA should be equal to the integral from alpha to beta of the integral of h1 of theta to h2 of theta f of r cosine theta r sine theta times r dr d theta. Okay, so before I was just doing this in terms of a polar rectangle. This no longer is in terms of a polar rectangle. This is any old polar region at all. So, but nothing really changes other than we've switched from doing rectangular integration to just doing general integration, except now this general integration, these two functions, are polar curves. They're not rectangular curves. So let's do an example of this where we're bounded between two polar functions instead of being bounded between just some polar rectangle. Okay, so let's do an example. So let's find the volume. Of the solid that lies under the paraboloid z is equal to x squared plus y squared above the xy plane and inside the cylinder x squared plus y squared is equal to 2x. Okay, so this is my function that I'm integrating under. Z equals x squared plus y squared. It's under this three-dimensional surface. It's also above the xy plane, and it's inside this cylinder. So what I really want to look at is, what are we talking about? What is this cylinder? Well, let's just look at this cylinder in 2 dimensions. So here's my x and my y. Well, what is this? Let's convert this cylinder into polar. So x squared plus y squared here, we know that x squared plus y squared is just r squared. And so r squared equals 2 times x, but x is r cosine of theta. I could divide both sides by r here and get r is equal to 2 cosine of theta, which we know is a circle of radius 1, diameter 2, sitting on the x-axis. It's not the prettiest circle I've ever drawn, but you get the idea. Okay, so this is 1. All right, so that's the cylinder, and if I had a z direction, this would be coming straight up. So if I were to redraw this a little bit in 3 dimensions, that cylinder looks like the following. Here's my x, y, and z. This is my positive x. This is my positive y, my positive z. And I've got sitting out here, we've got this circle. And so the cylinder goes up. And it's tangent to this z-axis, but it keeps going up and down forever. And then we've got some surface that is inside of that cylinder. Okay, some paraboloid that is inside of that cylinder. So we want to know how much volume is there sitting underneath this paraboloid inside this cylinder, or if you like, above this region that I shade in right here. Okay, but this is a nice polar curve as well. So we're really integrating above a polar curve. Well, which one? Well, that's it. It's r equals 2 cosine of theta. And I can map that whole polar curve is just between 0 and 2 cosine of theta. So let's set this up. Where do I start my integration and where do I stop? So I know I want to integrate with respect to some thetas, right? What thetas? Well, on this curve again, it's sitting out here. Where does theta start? This direction, right? And then I start picking up area until I get to this direction. So I start at negative pi over 2, and I end at pi over 2. Then I'm integrating from a function of theta to a function of theta. Well, really, there's just one function here. So I'm starting at theta equals 0, and I'm integrating out to this function, which is 2 cosine of theta. Okay. Then I know that I'm integrating under this paraboloid, which is x squared plus y squared, but x is r cosine theta squared plus y squared, which is r sine theta squared. That whole quantity needs to be multiplied by r. Let me erase my little picture over here. And then I get dr d theta. So this integral should get the job done for me. You'll find, just like other integration problems, that setting up the integral is most of the battle here. The integration itself, although sometimes time-consuming, isn't really that difficult, but setting up the problem itself is going to be the struggle. Okay, so let's do a little work here and simplify this. So I get integral from minus pi over 2 to pi over 2 of integral 0 to 2 cosine of theta of, now let's square these out and multiply through by this r. So I get r squared plus an additional r is r cubed cosine squared of theta. Then if I multiply through square and then multiply by r, I get plus r cubed sine squared theta dr d theta. Notice that I could factor out an r cubed here, and I just get cosine squared theta plus sine squared theta. But what's cosine squared of theta plus sine squared of theta? That's just 1. So this just reduces to integral from minus pi over 2 to pi over 2, integral from 0 to 2 cosine theta of r cubed dr d theta. Very good. Okay, so now this we can take the antiderivative of, and I get integral from minus pi over 2 to pi over 2 of the antiderivative of r cubed is 1/4 r to the 4th, evaluated from 0 to 2 cosine theta d theta. So let's plug in that 2 cosine theta and 0. If I do, by the way, I can pull that 1/4 out in front if I want to. So I get 1/4 integral negative pi over 2 to pi over 2 of r to the 4th. Well, if I plug in 2 cosine theta, I get 2 cosine theta raised to the 4th. And then if I plug in 0, I get 0. So that's it. D theta. We're getting there. This is equal to 1/4. Now, if I take 2 to the 4th, I get 16. That 16 can come outside of the integral. And then I'm left with an integral of negative pi over 4 to pi over 4 of cosine to the 4th of theta d theta. Okay, so outside you can see now I will have just a 4. And then on the inside, I'm going to need to use a half angle identity. Okay, so let me rewrite this. So now outside, I just have 4. And inside, I have integral from negative pi over 2 to pi over 2 of cosine squared of theta squared d theta, which is, of course, cosine to the 4th of theta, but that helps me to use my half angle identity. I have 4 negative pi over 2 to pi over 2 of 1 plus cosine of 2 theta over 2 quantity squared d theta, which is 4 integral negative pi over 2 to pi over 2 of 1. By the way, this 2 on the bottom, I need to square it. It'll become a 4. I could pull it out as a 1/4. Correct? So now I have 4 over 4 on the outside, and I just need to square the top. If I square the top, I get 1 plus 2 cosine 2 theta plus cosine squared of 2 theta d theta, which of course means I need to here use a half angle identity again. Okay, so this becomes 1, and I get integral negative pi over 2 to pi over 2 of 1 plus 2 cosine of 2 theta plus 1 plus cosine of 4 theta over 2 d theta by a half angle identity on this cosine squared of 2 theta. Now I think I'm ready to take an antiderivative. We might want to combine some things very quickly if we want. Maybe I will. This is integral of negative pi over 2 to pi over 2. This 1 and this 1 over 2 can combine to give me 3 halves plus 2 cosine of 2 theta plus cosine of 4 theta divided by 2, all of that d theta. Now I'm ready to take an antiderivative. Okay, antiderivative here is 3 over 2 theta plus antiderivative of cosine of 2 theta is going to be 2 sine 2 theta divided by 2, which of course means that those 2's cancel and I'm just left with a sine of 2 theta, plus, now we're going to get sine of 4 theta divided by 8, all of that evaluated from minus pi over 2 to pi over 2. Okay, so now I'm ready to plug this in. Let me erase a little bit here so that I can just do it up here on top. Okay, so now we're ready. Let's plug it in up here. First, we plug in pi over 2. So I get 3 halves times pi over 2. So 3 halves times pi over 2. Then I plug in pi over 2 here for theta. So I get 2 times pi over 2, which is pi. Sine of pi is 0. Then I get sine of 4 times pi over 2, which is 2 pi. Sine of 2 pi is 0. Minus, plugging in negative pi over 2, I get negative 3 over 2 times pi over 2. Then I plug in negative pi over 2 and I get sine of negative pi, which is 0. And then I get sine of negative 2 pi, which is 0. So I end up with 3 pi over 4 plus 3 pi over 4, which is, I suppose, 6 pi over 4 or 3 pi over 2. And that's my answer. Okay, so that's how we do double integration over a polar region instead of under like a general rectangular region. Now for some homework.